So, let's start properly now. Does anyone have any questions on the material of Tuesday? Short questions, big questions? Nobody? Everybody all completely crystal clear on things? Including notation and these sorts of things, yes?
Wait, I have one question.
Okay, good.
When we said that the vector from a different frame equals beta lambda times the b with the superscript, like this one.
Yes.
That one. Why? This is a bit like the other, like this one, right?
Yeah.
But why is there two subscripts there and a superscript here?
That is an extremely good question. Okay, taking the question. I'll get back to it in a second. Any more? I'm just stalling for time so I can look for markers in the meantime. That's a green one. Okay, thank you.
Sorry.
I'll find out.
That is a good question, yes. Let's see if we have any more. Usually it's a whole stash of markers here. Somebody stole them, okay. Okay, I have a green one. I prefer to have a black one for recording purposes.
If you want to, I can go get some from Debbie.
Well, I was actually hoping that maybe somebody could, or I can also do myself. Would you mind?
No, I can go.
Thank you.
I think the office is closed.
Oh, really?
You
can just go in lecture hall. Still a few there.
Okay, well, I'm sure we'll end up. In the meantime, we can work with this one. I'm going to make a bit of space because I already foresee myself dropping over things, which is fine. Relativity and gravity and such. That's a nice demonstration. Very good for my bones. Okay, so Joyce's question has something to do with this. That what we derived was this. Yes. Now, just to warm up a little bit, what does this mean physically? What does this tell you? This relation?
That this lambda mu nu is a Lorentz transform.
And then the thing is invariant?
I see no particular invariance here. Oh, that's a huge stash. Where did you get it from?
Lecture hall 09.
Okay. Notice the slight hesitation in answering. Yeah. Okay, so, all right. So that this is a Lorentz transform, sure. I enjoyed saying something about invariance. Why? Where? How?
Yeah, actually I don't know. Cause no, not this. No.
Okay. No, I'm not saying that you're wrong. I'm just curious where you got it from. Because
yeah, I just got it from because the one is from one frame, the other is from the other frame, and it just transferred.
Okay. Well,
but it's a different superscript.
That is true, but there is a particular amount of invariance here. Now, first physics. Yes, the physics, of course, this is a Lorentz transform. This thingy B, as you know, is a collection of 4 numbers that have a very particular relationship. Namely, that if you would measure those 4 numbers in one coordinate frame, and you would then go to some other guy's coordinate frame by Lorentz transform, you would end up with this one. So this is the original one, 4 numbers that you've measured. You measure the same 4 numbers in another coordinate frame, you end up with this one, and their relationship is exactly this tensor here. That's called the Lorentz tensor, yes? And it's just a new notation of writing down those Lorentz transforms that you're all familiar with and know by heart and all these things. So that's what that means. The question that we now got, or no, let me go to Joyce's comment first. There is a contraction here, yes? That's in the news. Now, if there's one thing you have probably picked up from our meeting of Tuesday, is that contractions come with a very special property. What is that property? So you have one index downstairs, one upstairs, you contract them, and as you know, contraction means let this mu take all its 4 values and add everything together. That particular sum of products has a property.
That's invariant.
That it is invariant. Now, when she said, oh, there is invariance here, the first remark that I made was, no. That's because invariance in equations like this has 2 slightly, subtly different meanings. Well, first of all, one meaning is, are these four numbers invariant? Are these four numbers the same in all corner frames? No, that is certainly not true. That's exactly what this relationship tells you, that they're different. Yeah, so in that sense, I dismissed the idea that there is invariance. So, but there is a second type of invariance here, namely that the relationship itself, the whole equation, is invariant. Do you see the difference between those two statements? One of them is, are the numbers the same? That answer is no. But in a somewhat more deeper way, is the relationship between numbers, is that the same? So the numbers themselves are not, but the way that the numbers are related to each other, that one is invariant. And that is indeed because of this contraction. Now, something would be very wrong in our relativity if we were to write down an equation that would not be invariant. Again, the numbers are allowed not to be the same, but if the relationships are not invariant, you're breaking relativity from the outset. If there's one thing that relativity always tries to maintain, that it is that there are relationships that are the same in all coordinate systems. Okay? You might remember from special relativity that this is what you call the principle of relativity. It's not that all numbers are the same in all coordinate frames, it's that relationships are the same. You will be in a very strange situation where some law of physics, give me a law of physics, doesn't matter which one, any equation that from any, sorry?
Newton's second.
Sure, Newton's second law, there you go. That one. Is this one invariant, the way it is written down now? No. That means that if you were to use this law in one coordinate system, it would produce the correct physics, it would give you the right accelerations and the right things you can measure and test with experiment. If you would go to another coordinate system, you would find, if you would try to apply this law, right, you would get a different acceleration, the force might be different, but then you end up in a situation where this law gives you answers that are actually wrong. And that would be very strange, because that means that this law only applies in one coordinate system and not all other ones. That's fine. Nature could have been that way, that there is one coordinate system in which everything is, in which you always have to calculate your laws of physics. In fact, this is what people thought before Newton. Right? This is Aristotle, his quote-unquote physics. That he said, well, there's this one coordinate frame. He never put it in those terms, but this was his thinking. There's this one coordinate frame from which you're only allowed to do your physics, namely the Earth, because the Earth is the center of the universe, and of course all the rules apply there, and all other coordinate frames are wrong. It was Newton who came with the idea, no. In fact, there's more coordinate systems that all of them work. Now, Newton did not make the full step to relativity because he didn't know about the relativity effects, the speed of light and such. But it was Newton who realized, no, all coordinate systems should be okay. Now, this law does not apply in all coordinate systems. Okay? So that means if I were to build a theory of relativity, by which I mean some theory of physics that works in all coordinate systems, this one is disqualified. This one is not, because it has a contraction. The numbers are different in coordinate frames, but the law is the same. Okay, so in that sense, there is invariance there. Now go back to Joyce's question proper. I'm paraphrasing, so please correct me if I misunderstood your question. Her mentioning was, look, we have this relationship between one 4 vector and another 4 vector, and there comes this tensor in between. Fine. But we also discussed another one, and here's one, for instance. Let's do this one. You'll remember this one, right? And there's also contraction here, right? In fact, there's two contractions, over nu and over mu. So this is double invariant, if you want.
Isn't there a minus?
Yeah, that's true. I'm sorry. That is true. No, you're completely right. It's text dependent. Some authors put the minus sign someplace else, and I always have to correct myself. This is my minus. You're right. Now this is a double contraction. Yeah. And her question, and again, this is where you might have to correct me if I misunderstood you, is here's a contraction that gives you a thing, here's a contraction that gives you a thing. Why are the two numbers here? Yeah. One up and one down, and here they're both down. What's that about?
Is it because you only contract the new thingy and you just put the other up?
Now that is certainly part of the reasoning, yes. Anyone an answer? Possibly. I mean, do you see the question? Why would you write a contraction here with one up and one down, and here you have a contraction and you decide to put them both down. Well, why, how?
Well,
Is there a difference?
what would the mu be contracted with? Because B isn't in relation with
Well, that is certainly true.
it, so like there's no way to contract your mu really. So why would you put it down?
But then if you put it up, does that mean you don't do anything with it? Can you just randomly say?
No,
okay,
that's your question, I think. I mean, this.
Because I was thinking the
why
same,
is
like
not-
you're not contracting it, but
Yeah,
I was wondering if you
okay,
could
I
just
see,
put it
yes.
up then or something.
So, can I rephrase the question by saying why is this not correct?
Yeah.
Now, immediately I can tell that there's something wrong with this equation as it stands now. It has nothing to do, well, it has to do a little bit with physics. Can you tell what, suppose that I would take this one down, can you tell me what is wrong?
Well,
You will make it from covariant to contravariant, so you have contracted it with a eta,
Ah, yes,
and
yes.
so it's not the same anymore.
Well,
Eta mu nu.
this thingy, and you gave the right answer. This thingy here has its mu downstairs, yes? But that means that this whole object, in its mu-ness, is a covariant thingy. Agreed? Yet this is a contravariant thingy, because it has the mu upstairs. So immediately you can tell something is wrong. Now, covariance and contravariant are not just notational issues. It really has to do with physics. Do you remember what the difference is between contravariant and covariant? What is the difference between B with a mu upstairs and B with a mu downstairs?
Wasn't it the sign in the Lorentz transform?
Yes, exactly. Exactly. So apparently, if I were to write down this, yes, and I would measure my 4 numbers, and I would go to another guy's coordinate system, then this side of the equation would transform, but with this minus sign maybe in your Lorentz transform, and whereas this one would also change, but with the plus sign. Well, then something goes wrong, right? Because it might have been correct, this equation, the equality in one coordinate frame. I go to another coordinate frame, but both of the 2 numbers, left and right, change in a different way. And that means that all of a sudden it's not correct anymore. So I can immediately tell, no, something is wrong here. If the mu here is upstairs, it must have been there. And that's all there is to it.
So it's just definition.
could you write both of them down?
You could write both of them down, and this was what Marlijn was saying.
Okay.
Suppose that for some reason you have a super preference for covariant vectors, yes? You really hate it when those damn indices are upstairs. Get them down as quickly as you can. How would you get those mu's down? Suppose I want to write down this, but now in their mu-ness it must be covariant. Yes, covariant. How would you do this?
Same way as you do it.
You use Minkowski.
Yes, that's another thing I hope you've picked up from 2 days ago.
Sorry.
If you want to get indices upstairs and downstairs, you do this by contracting with the Minkowski tensor. So, let's turn this one into the one that she prefers, namely with indices down, the mu's down. How do we get this mu down? So I want to have one that's called alpha now. How do I get the...
Let's add mu alpha both downstairs contracted with the b mu.
There we go. This one, or this one, is given by the contraction of this one with the Minkowski tensor, yes? Now this is not trivial, I'm just repeating myself a little bit from 3 days ago. We have defined a covariant 4 vector as one, indeed, where there's a minus sign difference in the Lorentz transform. But we proved, that was one of the exercises that we did in the tutorial, that that's the same as taking your contravariant one and contracting it with the Minkowski tensor. That is not trivial, yes? Without that proof, you have 2 separate statements, namely covariant means contraction with Minkowski tensor, and a separate statement is covariant means Lorentz transform with an opposite sign. We have proved that that is the same statement. So, if you want to get this one down, you want to turn this into a thingy that transforms with an opposite sign in its Lorentz transform, do a contraction. We have done it to this side now. So, what happens to this one? So this is left-hand side of the equation. How about the right-hand side?
You contract with this same
Of course, but you do whatever you do to the left-hand side of the equation, you also have to do the right-hand side of the equation. That's not even relativity. That's just maths, okay? So we also contract this one, mu alpha, here's the Lorentz tensor, alpha, no that's not alpha, excuse me, nu, be nu, okay. What do I get?
Lambda mu nu
Yes.
downstairs.
Now we
no,
get
alpha nu.
alpha, of course, yes. And so we know how to get the mu's down, just contracted the Minkowski tensor, combine these two, and I'm now in a place where I can write this into the, it's called the Cobuson form, by which is meant all indices down, and you will get indeed this. Okay, you will get this. Now, notice that this Lorentz tensor has now changed. Not just in notation, physics in the thing has changed. Indices up and down is just not a notation, it means now all of a sudden there's an extra minus somewhere in your Lorentz transform. So this really, despite both of them being called capital Greek L, is really a different thing than this one. It really means something else. In fact, let's make it a little bit more beautiful here. And that really rounds up, brings everything full circle to our lecture of 2 days ago. This is correct, this equation, but there's still one of those damn indices that is downstairs. There's upstairs, okay? Now suppose I want to bring this one downstairs. Suppose I would like to do that.
You shouldn't.
Sorry? You shouldn't. No, of course. Listen, this is correct, this is correct. So I'm not reading, and I'm just rewriting stuff, okay? But there is a point to be made to make sure that this nu goes downstairs, and that is that what we now have, or let me start here, what we originally had was if you have a contravariant 4-vector, you could calculate how it transformed to its contravariant version in another guy's coordinate system. That's what this thing told you. All right? What this thing tells you is I take a contravariant 4-vector and want to see what it looks like in somebody else's coordinate system, but what this equation tells me, it gives me the covariant version in the other guy's coordinate system, which is not wrong, it's just probably not what you're looking for. Right? What you want is relationship between one guy's covariant to one other guy's covariant. We now have the relationship between one guy's covariant to one other guy's contravariant. Not wrong, probably not very useful. So there is something to be said, you know what, let's make a relationship between contravariant ones.
I think then you would have to put the nu and the lambda upstairs, otherwise you cannot contract the two.
You could just multiply it with the Minkowski.
Contract, yes.
Well, yeah.
Yes, okay.
Right.
Yeah, no, I already promised I'm going to be strict on that, okay?
No, I mean you can just contract the B of nu with, like B nu with the Minkowski.
Sure.
But then you bring the other one
Yeah,
up.
then the other
Yeah.
one goes
There
up
you
again.
Because you have to do it to both sides. You cannot.
Ah, yeah.
Yes.
But you can change the lambda nu upstairs and the b nu downstairs.
Look.
Oh, yeah, that's true.
What you could do is, if you're not seeing this step immediately, trust me that it is correct, and we can talk about why it is correct. You can switch those two around. In a contraction, there's always one up and one down. You can always switch them around and you get the same thing. And you might want to think about why that is. But suppose that you can, and yes you can. Now we are in the situation where indeed we have the whole relation now covariantly, thank you. We have now the same relation covariantly. Now, of course, there's always going to be one upstairs. Whenever there's a contraction, one has to be upstairs. So this idea that we should get all of them down, that we cannot do. But we can make sure that at least the vectors that we are transforming, all of them are either covariant or contravariant. Now, I promised you to make a little bit of full circle to the lecture of a couple of days ago, because look what we have here. This is the relationship that tells you how you make a contravariant in one system into the contravariant of the other one, and by definition of 4-vector that goes with the Lorentz transform, yes? Do you remember what by definition a covariant 4-vector does when you go from one system to the other? We already answered, in fact you did. But do you remember how covariant 4-vectors transform between coordinate systems? If this one goes with the Lorentz transform? The contravariant ones, how do the covariants transform?
The plus one.
Yeah, opposite side.
With the opposite sign in the V, yes? But don't we exactly, what we have here is the relationship between covariance between coordinate systems, right? So I can sort of already guess that this new matrix is not the same as this one because the indices are at different places, but I can already guess that this must be the same thing with the V switched. Do you see the logic here? We started with this one. By definition, this is the relationship between contravariant between coordinate systems. We massaged it using a couple of contractions into its covariant version, but we know that covariants transform with the opposite sign in the Lorentz transform, so this must be the Lorentz transform with an opposite sign. Shall we check whether that's the case? Just to see whether these machinations that we did here really gives us this thing with opposite signs. Alright, so my question now is, we have this thing, alpha nu, and we want to see whether it is this matrix, the same thing, but with minuses extra. First of all, how do we write this in terms of this? This is my strategy. I'm going to take this one that we know and going to massage it to this form and then see whether minuses has changed in the right positions. How do I make this thing into that thing?
Two Minkowski metric.
Exactly. Two contractions, yes? Because this one has to go upstairs to make sure that you have one index up, the first index upstairs. This one has to go downstairs to make sure the one is downstairs. So you need two Minkowski metrics. One of them to get the index up and one of them to get one down. So you tell me, good exercise in getting indices right. So yes, we're going to take this one, mu. I'm not going to call this one nu now, by the way. Let's call beta. Do you see why? I mean, I copied this one and put it here because this is the one we're going to do something with, but I decided not to call this one nu anymore. I called it beta. Why did I do that?
You get ambiguity in the etas if you do that.
Yes, because there was already a nu. And if we want to call that one nu, first of all, that would be wrong because one u is upstairs and one is downstairs. That would be wrong by itself. But also the etas that we're going to put, we're going to have multiple nus now, and which one goes with which. Okay, so let's switch the notation. All right, so we already predicted we're going to need two contractions with etas, but we have to get those indices right. So you tell me, where goes which?
The beta nu upstairs.
Yes, because this one now will make sure that this beta will go upstairs and be turned into a nu, and that's what we want. So that one is correct. Good. How about the first one?
Alpha mu.
Alpha mu.
Curious who that's going to be. I'm thinking Raquel. No, hey.
I'm really sorry.
Oh no, that's fine. It's just you have what's the opposite of luxury?
Sorry.
That you don't have that you might have difficulty finding a place to sit.
Yeah.
All right. So yeah, what we can do now, right? Our object was that we have a very strong suspicion that this matrix that we have ended up with, see now being sloppy myself, this tensor that we ended up with, is really this one, but with the minuses, extra minuses in front of the v's. And then I said, let's check that. So let's calculate this thing. How do we calculate it? Well, it's really this thing with the indices switched, and that required two contractions. We can go through this calculation, and then we just literally get this matrix, quote unquote, and then we can just literally check whether it is the same Lorentz matrix but with minuses. Feel I go through the calculation? Just to see whether everything checks out and works out. We all see the strategy here, aside from the stupid algebra and such? Okay. Then I'm going to erase the rest of this. actually want to save the final equations. Somebody asked me some time ago why in Physics 3002, special relativity, I didn't just start with tensors. I hope you see that there is a point to first learn how to do it and then only later put the tensors in, okay? But we were doing secretly this stuff all along. Okay, now, let's copy here. Hoping that somebody's going to make a comment now. Nobody? No? I just copied this one here, so I have a little bit more space. No comments? Really? Nobody's?
No,
yeah,
you switched
they have
them
to-
around.
Is that a problem?
No.
Okay, are you sure? I mean, you can tell by the tone of my voice that it's not a problem. But,
Yeah.
can you see why?
Yeah.
This is like a diagonal matrix, right? Switching, the indices just means switching rows and columns, but it doesn't matter for a diagonal matrix. So. Or symmetric matrix, I should say. Okay. Now, alright, now comes the point where we just really have to write out stuff. So that takes a little. So we might not go through the whole calculation just to see. Depends on how long it's going to take. Well, we have two contractions to go. We have this one and that one, and then we have this one and that one. Any preference for which one to start? No. Alright, let's write down this. Oh man. Let's keep the alpha as is. The mu has to go through its four values, yes? 0, 1, 2, 3. 0. This I'm not doing anything with yet. 0. Beta. That's 1. Alpha 1. I'm very regretting that I suggested that we go through this exercise.
Pretty sure you're gonna run out of space.
Take forever.
Yes, but fortunately, yes, that's true. Okay, that's the beta contraction. Okay. Now what? How many numbers do we have to check in the first place, by the way? How many equations are this to begin with?
16.
16, right? So we have 16 equations. Mind you, each of these equations comes with, well, one contraction is already 4 terms. The, what was the other one? The mu contraction is also going to give you 4 terms, give you 16 terms. So we have 16 equations, and each of them has 16 terms on the right-hand side.
I mean, all of them except for 4 drop out, don't they? Again, because, well, diagonal matrix. So.
Whoa.
No,
No,
it's
not
the
really.
Minkowski.
Oh
This
yeah,
one
yeah, I know those. Yeah.
was gamma minus gamma v minus gamma v gamma 0 0 0 0 1 1 0 0 0 0 0.
Yeah.
So there is some drop outishness. That's true.
No, I will still have Minkowski.
So I suggest we do the following. If you want and you really have nothing else to do, yeah, you can spend a beautiful day. Well, it's not that long, but I mean, there's many zeros and such. But you can spend some time working out those 16 equations, each with 16 terms. But for our purposes, really, we're only interested to see whether this matrix, the one that we're calculating now, has opposite signs here. That it's like this thing, but with pluses. Okay. So maybe what we should do is just check these ones. Now, the rest you also have to check, yes? But then again, that's 16 of these things, and I don't think we have the time, there's not much physics there. Let's just check whether indeed these minuses have changed, and you can do the rest for yourself if you want. So, of these 16 equations, which one are we going to check?
0, 1, and 1, 0.
Yes, so let's go with the 0, 1 version. Right. And maybe we can be even a little smarter here. Because you see, the original matrix that we started with is diagonal, yes? So it means rows and columns. You can switch freely. Well, that is the question. Is the new thing that we calculate, is it, if,
Oh, yeah.
well, if that one is also symmetric, we don't have to check 16 numbers, because if you have one half of it, the other half is just the same. So we might only have to check this one. Well, let's do that one. 0, 1. Okay. So, oh, that's actually good news. Look. What happens to alpha for 0, 1?
Zero.
Yeah, that's 0, but we also know the value for
Gamma.
at the 0, so it's not gamma.
It's
No, you're confusing.
Oh,
transfer
yeah,
now,
the-
yes.
It's
Minus
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 one.
1. Okay, so that will give you, this one is still there. Here's your 0 still, and here's beta. Oh, but nu we also gave a value, yes, that was number 1. So this term has become that term. Now note there's still a contraction though, but that contraction should in principle give you 4 terms. We can also do away with, right? Of these 4 terms in beta, which beta is the only one that survives? Yes, exactly, that's the beta is 1. It's not because of this, that's because of this. Right? Eta is diagonal, and in the one row there is only one column that does not have a 0. So the only beta here that survives the contraction is when beta itself is 1.
It's going to be
And then this is going to be
yeah, just 1.
just
And
1,
you
right?
have
So
the
the whole
minus.
thing will become 1, and then this has become a 1. So we know that all of this is 1 times the 0, 1 of the original Lorentz tensor. Let us put in the Lorentz tensor values in a moment. We can do the same reasoning here. Let's be very quick about this. Alpha we had set to 0, yes? So this is a 0, and this mu that was a 1. Here's a 0, and that is a 1. Here's a 0, and that is a 1. Okay.
All to 0, yeah.
Yeah, they're all 0, right?
Mm-hmm.
Okay, good. So of these 16 terms, only 1 survived because of the many zeros in both this matrix and in this matrix. All right, now, so plus 0, 0, 0. Okay. Minus 1 times the 0, 1 of the original one. 0, 1, that's this one.
Just gamma v.
That gives you gamma v. And that's
Makes sense.
that makes sense. That's exactly what we were expecting. Our whole object was to find that this one is the Lorentz transform with an opposite sign to the v's. Well, at least for one of the terms, we have checked this.
I'm still a bit confused because I thought with 1 eta you would already change that sign, but then when you use 2 etas, it would make sense to me that you cancel it out again, changing the sign. You see what I mean?
Yeah, I see what you mean, but it clearly did not happen. Let's see what we did here. I mean, what we did was correct, yes?
Mm.
But your question was you have 2 etas, so you expect 2 minuses to pop up.
Yeah.
Yeah, but yeah, no, that is true. But the only way that an eta can give you a minus is when indices are all 0, right?
Mm-hmm.
That's the only way that this one, that an eta gives you a minus.
Mm.
But our nu here was a 1.
Mm.
So that means one of the 2 etas was in one of the rows that did not contain minuses.
Yeah.
But I think I see his point where he says like you will change the minus, but the thing is you see that one eta has both indices down and one both indices up. So one changes the sign of the first row and one changes the sign of the first column.
Mm.
So you see that that's exactly what happens because the first element is common to both.
Mm.
So you would have minus minus, it becomes again a plus.
Mm.
And then you have the first element, the second element in the first row is minus and the third.
Makes sense.
So the first one cancels out, that's why.
Now, this matrix that we were looking for, I keep saying matrix, but you know what I mean. This is a sloppy notation that you'll end up with in general relativity. Now, what we've checked, that this thing that we were now calculating, the one that we clearly suspect is going to be the Lorentz transform with an extra minus in front of the v's, we have found that this entry here, the 0, 1 entry, indeed is plus gamma v, exactly the opposite as this one. If you go through this calculation for all the other 16 ones, there's still 15 remaining ones, you will indeed find that you end up with this. Exactly what we were expecting. So it's completely full circle, everything works out. Are you okay, Colby?
Yeah, it's okay.
So Joyce, very long answer to your question, but I hope the overarching point here is there is a difference between thingies upstairs and downstairs. Okay. It's just not just notation, it's not just contraction with etas. You actually end up with correct physics if you do it correctly. Good. Oh, one final physical point. We made this point in the tutorial as well a couple of days ago, but we now know that this is transforming to some other coordinate frame with a minus sign. This one we have checked. If you go through all entries, all 16 of them, you find this is the one where you transform in the other direction. So if you want, if we would lay out the coordinate system here, here's an x-axis. Here's 4 numbers that I'm measuring, okay? And I'm measuring these 4 numbers now. Pop, 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 get my 4 numbers, my b's, those b's. Now I move to some other guy's coordinate frame, measuring the same 4 numbers, I would end up with this one, yes? And that would give me the Lorentz transform in between. So this is how I can get those 4 numbers to these 4 numbers. But this one, because of this extra minus sign, is transforming back. Because if I am moving in this direction with a certain sign in my v, then transforming back just means transforming with the opposite sign, yes? So if this one gets you from this coordinate frame to this coordinate frame, then this tensor brings you from this coordinate frame back to the original one. That makes perfect sense, right? One of them you go minus v in that direction, the other one gives a plus v back. It's the same as if you never moved at all. In other words, this is the inverse transform, Lorentz transform. That also means that if you would take this matrix, and you would multiply them with each other, now I really do mean multiply, matrix multiply them, what would you get? The combined effect of first transforming to this guy's coordinate frame, that's this tensor, then going back to the original one, that's this one. If that combined effect, how will I write that itself as a matrix? The identity matrix, right? Yeah. You can check for yourself that if you just take your linear algebra, forget about tensors and such, take this matrix, take this matrix, and yes, I do mean matrices now. Matrix multiply them with each other, you will get the unit matrix. So, or if yes, and if you want to do it in tensors, it will get you a Kronecker delta. So it makes sense on all levels: physics, mathematics, tensors.
How does a Kronecker delta look as a tensor?
The student matrix.
Oh, okay. So yeah.
And that's just a tensor way of writing unit matrix. All right. That's a nice way to wake up, right? Nothing like some people wake up, do 50 push-ups, some people drink coffee, and other people work with tensors. Well, and some people do all 3 of them, by the way. Not naming names. Okay. So, any more questions? In all seriousness, this is stuff that you should not have too much. I mean, of course, you can take a while to work out things and how do things work, but this is stuff that at some point should become very natural to you. Yes, this is the kind of work that we're going to do extensively when we do full general relativity. Okay, now let's do an exercise. Are there any preferences? Because I have a particular flowchart in mind, but I'm happy to accommodate if people have particular questions. As in, I would like to do this exercise rather than the other one or so.
I didn't look at them yet, so
well, let me divide the exercises in 2 parts. A couple of exercises that I gave were from chapter 4 in Hartle. And chapter 4 is just on special relativity, not even in tensor notation, it's just really special relativity. And I gave those exercises just to get you reacquainted with the concept of time dilation and such. Okay. In that sense, there's not much new physics here. Then I gave a second set of exercises about chapter 5, and this is where tensors do become important. And so I have a preference for exercise of chapter 5.
Yeah.
But this is mine, unless people really want to look at the
Can we do
Well-
chapter 5? Because
5.
4 is just review.
I didn't understand 4.18, but if you say it's less important to understand
We
these
go on
things,
check.
then I'm fine with going to 5.
Well, the nice thing about having tutorials with small groups is, of course, that we can easily accommodate. For 8, calculate the hyperbolic 18. Okay, because a hyperbolic angle. No, we have actually done this in special relativity, but I didn't name them as such. A Lorentz transform can be written as if you rotate in space-time, but the axes are curved, right? They're twisted, skewed. Minkowski time diagrams, and that means that you need a special angle to make that work. The sine doesn't work exactly this way. That's the hyperbolic one, but okay. 18, you said. You showed that for 2 time accelerated events, there is some inertia frame in which, oh, that is a cool exercise though.
Yeah, I was just confused about the time-like, space-like.
About the terminology? Or what it
Yeah,
means?
the terminology, what they meant by this.
Okay.
It's with the cone, right?
Sorry?
It's with the cone, right? Like on the C word line, it's like light-like, and then in between, I think it's space-like, and then outside time-like, or something like that.
That's correct. Yes. But that's one way of visualizing it. Time-like means that you, in terms of Minkowski space-time diagrams, that means that you have 2 events, one of them within the light cone and one of them out. Okay, that means that's another way of saying you cannot, with the speed of light, cannot connect these 2 events. Space-like means any 2 events within the light cone. Physically, that means 2 events. Then
I thought the time-like means there is consequence between the 2. Like one causes the other, and space-like it just means one happens here, one happens there at the same time. It's space-like. So there's the black here.
did I mix up the terminology here?
I think you said
No.
that time-like means that it's faster than the speed of light, but I think it's the other way around. Because space-like means they're at the same time, or they could be at the same time in 2 different locations, so it's faster.
No, the space-like means that you can find a coordinate system in which they are at the same position, yes? So that you can find a coordinate system where you go from one to the next. But this is just terminology.
Yeah.
The bigger question here is there's 2 ranges of your space-time. You either have 2 events that cannot be connected because they're separated by the light cone, right? They're not in each other's light cone, and there is one that says you can have 2 events that are within the same light cone and therefore can be causally connected. Now, physically or mathematically, that means that either your Minkowski space-time interval, your d tau, is a negative or a positive number, and if it's 0, then it's called light-like. And the only thing that it says here is
Just a question, what page is the exercise?
Sorry, this is page 76 in my version of the book.
Yeah.
It literally says if you have a space-like interval, show that you can Lorentz transform yourself to a frame where those 2 events happen at the same location. And if you have this time-like, then you cannot do this.
Yeah, that makes sense.
So it's an exercise in either if you can draw it out by Minkowski space-time diagrams, or you can just literally do it by Lorentz transforms. If you want, you can do it by tensors too.
So
mostly better
you try to get the x prime to become 0
Yes.
in a Lorentz transform.
So yeah, exactly.
Okay.
Your dx prime.
Yeah, with a positive dx non-prime.
Yes, exactly.
Or negative. Just
So
anyhow.
the question really is, if you have your Lorentz transform, so dx prime is gamma dx minus or plus or so phi dt, and then you have the other one for time as well. Is there a solution possible that makes dx prime 0?
Okay.
Given that the 2 events that constitute the dx and the dt, that those are space-like separated. That is the question.
We don't have to do that exercise, I think it makes sense.
Okay. Then I propose to indeed go to chapter 5. There's this beauty of an exercise. I really had a lot of fun doing this one. So I always write out the exercises before the lecture series starts, but on the train, typically on my way to here from Nikkev, I tend to, where's the wiper? There we go. I tend to redo them. And yesterday, I was taking a train from Nikkei back to here, snickering all along because of this exercise. People were looking at me funny.
Which number is it?
I haven't specified yet, but it is going to be from chapter 5. But the exercise that I would like to go to is exercise 6 I would like to do. So for the people who have the book or a PDF in front, it's page 100.
Thank you.
In my book it's 100.
Okay.
We all have the theme?
Can you, why did you put the exercise we had to do? Because I didn't see
I put it in an email.
Oh, yes. That makes sense.
And the book itself is under course materials.
What is it here?
Alright, so in my email I first, as a warm-up exercise, asked the following. Right. Show that this thing is a 4-vector. That should be easy. This is by definition this object. Argue that this is a 4-vector. It's not a 4-vector, it is of little use in special relativity. What is a 4-vector? By definition.
Transforms by Lorentz transform.
Okay, so we have to check whether this thing transforms. If you go to some other guy's coordinate frame, you end up with mu primed, this one. Is that given by gamma mu 0 plus or minus or so v u1? That is the question. If so, this is a 4-vector. That's the definition. Or, you know what? Let's write it in tensors. Is this true? Only if this is true, or equivalently this one is true, then you have a 4-vector. Is this a 4-vector? Should be very easy, this one.
I mean, you know that the denominator is just an invariant,
This is invariant.
so it doesn't transform at all.
This one doesn't transform at all.
You know that the numerator transforms as a 4-vector,
Okay.
so
That's all there is to it, yes. You know that this one transforms as a 4-vector. And okay, sure, you divide it. Mathematicians hate it when you say it, you take a derivative, but you divide it by something that does not change at all between coordinate systems. And that's all there is to it, right? If this transforms as a 4-vector, and you divide it by something that does not transform at all, you end up with something that transforms as a 4-vector. All its transformation properties cannot come from the denominator because it doesn't transform. All the transformation properties come from the numerator, and the numerator transforms as a 4-vector. So, yes, this is a 4-vector. That's good. So we know that this holds for that one. Then as an immediate follow-up exercise, I said, well, calculate the contraction with the thing with itself. By this I mean this. Contract the thing, the contravariant version of the thing with its covariant version. Now, before writing out what it is, what can you immediately say about whatever this combination is? Something will come out. What do you know about that combination? It's invariant. So if somebody were to measure a 4 velocity, construct this number, whatever it is, and you ask, that the person asks his homeboy to do the same exercise, but doing it from a different coordinate system, he will get different numbers for these, but their combination is going to, this contraction is going to be the same number. By the way, what does this thing mean? It's sort of like a velocity, but not really, right?
Proper velocity.
Well, we call it a 4 velocity, or the proper velocity, or whatever you want to call it. Well, there's Marit walking down in Severin, right? So let's take 2 moments of them walking through a courtyard as events. First they were over there at Osa, and now they're at the coffee machine. Those are 2 events. Okay? The dx tells us something about what the distance is between those 2 events, namely the amount of meters that they have walked. The d tau, what does that tell us? Yes, but whose time, right? It's
For the
relativity.
person at which the return
That's correct.
happens at the same.
I got one good answer here. Okay.
Their own time?
Their own time, yes. It's proper time. So it's sort of it is velocity, but it's a strange velocity. I take how many meters I saw them walking, divide by how many seconds they thought they were walking. Now, in Newtonian physics, that wouldn't be a problem because my time is their time. Special relativity, not so much. So this is a strange object. I measure how many meters they've walked. I ask them how many seconds that took, and then they take those two numbers. So it's a little off, right? I mean, they take a number from my coordinate system and a divide by number from their coordinate system. It's like a bastard object. I mean, if I want to know how fast somebody's walking, I take my time or my duration of them walking and the distance that I see. But this is a strange object. Now, why on earth would somebody be so hideous to use this particular type of velocity and not, normal velocity like this one? I take my time and my amount of meters. Any reason why people in special relativity prefer this one over the other one?
Or it's 4 vector.
Because it's a 4 vector. Because it is a 4 vector, you can make invariants out of it, and invariants are good. Invariants are your best friends in special relativity. You don't have to worry about what they look like from one frame to the next. So we're sort of forced by necessity to use this one. So yeah, you were.
It's probably going to be wrong, but could you argue that because you're contracting with the upstairs and the downstairs, it's going to be like, well, going there and then going back, so it comes out to be 1 again?
Well, what you're now saying is really a verbal representation of what it means, a contraction. Because one of them, if you go to another coordinate system, this one transforms with a plus sign, the other one transforms with a minus sign, and they cancel each other out. So what you were just verbalizing is just another way of saying that this is invariant.
Okay, yeah, true, isn't it? Yeah.
Gideon?
Yes.
So velocity is not a 4 vector,
This is not a 4 vector, no.
which is a velocity, right?
This is just velocity as you would measure it if you see a car passing down the street or so.
Yeah. But
That is not a 4 vector.
momentum is a 4 vector, right?
If I were to make this into momentum, it is still not a 4 vector.
Then what momentum is the 4 vector?
Because it doesn't have the right properties, right? This does not have the right transformation properties, so n times this does also not have the right
But we
properties.
said
The left one is the 4 momentum, if you multiply that.
So you okay.
So yeah, we make a momentum out of this one, n times this strange
the one we
velocity.
used the last tutorial was the last one, right?
Yes,
Okay.
and not this one. So yeah, this is the more natural thing. If you're doing measurements, then you're going to take your amount of meters and your amount of seconds in all of it in your coordinate frame. But unfortunately, nature has decided that this thing, although it's the one that you measure, is not the one that leads to invariant quantities. Now let's calculate this one quickly and then have a break. Let's write this out. Or does anyone already know what the answer is, by the way, to this?
It's minus 1.
This is going to be -1. But maybe it's good to go through the exercise, right? Now,
So,
you tell me.
okay, so that's what
It's the same as this, as you know now. There's a double contraction. Somebody dictate what happens now, okay?
Do we need to go through it?
Sorry?
Do we need to go through it all again or not? Or just assume?
I'm missing the first part.
Yeah, just because it's just a double contraction, you just need to fill it in, right?
Yeah, we just have to. Oh yeah, yeah.
And then it's
yeah.
just like all the
There we
numbers
go.
again. Some of them
How
just
many
zero.
terms, unfortunately, do you end up with? If you were 16?
16.
Yes. But if you didn't know about what this tensor was, you
Yeah,
would
but
end up with
all of them
16, yes.
becomes most of them
Now,
become
how
zero.
many, fortunately, because of the form of this thing, will you actually end up with? How many terms? It's going to be 4. In fact, it's a double contraction, but you already know. I mean, you're free. I mean, you're happy. I mean, feel free to write out the 16 terms, but you can already tell. No. But I know that this one only gives you something if mu is nu. Okay. So instead of doing 2 contractions, one from mu, one from nu, you might as well immediately do both contractions at once. This is -1. Well, this is dt d tau squared. This is 1, that is 1, that is 1. So it gives you dx d tau squared. This is dy d tau squared, dz d tau squared. The sum of their squares, if you want, is just this one, right? And this gives you dx d tau squared, dy d tau squared, dz d tau squared. If I'm not mistaken, this is just Pythagoras theorem. So it gives you just the total length of this vector. Okay. Hey. Well, Simon's claim is that it should be -1. I'm not seeing a -1 yet. I see a minus. I mean, we're getting there, but
So 1 over gamma squared.
1 over gamma squared?
Yeah.
Why?
Because the d tau gives a gamma. Oh no, the d
dt
tau gives
over
1 over
d2.
gamma, so then it's gamma squared. Yeah.
Right. Do we all remember from special relativity the d tau that there is this time dilation that tells you dt is gamma d tau? Alright? That means this gives you gamma squared. Okay. Now how about this one? dx d tau.
Sorry, where did the dt equals gamma d tau relation come from?
That is from special relativity.
Ah, okay.
Yes.
Makes sense.
It's a gamma squared multiplied by the normal velocity. in the
I
x
very
direction.
much agree with that. Do you see this? The people who are not seeing this, there you go. No, maybe it's just we're not so quick to fill out the details. So you see why, but why is this?
Because the d tau again gives 1 over gamma squared. Yeah, 1 over gamma.
Oh, it's like what we did.
And because it's on the bottom, it just gives you gamma, and then you get dx dt.
So that's applying the chain rule here of differentiation. The derivative with respect to tau is the same as dt d tau times dx dt. dx dt gives you v, but dt d tau gives you gamma. So this gives you this. So I see something beautiful happening here. I see something more beautiful happening here. Just put in what gamma is. Now you have your -1. It's not just -1, it's an invariant -1. It's going to be -1 in all systems. Well, Adrian looks very happy now. All lights up. Okay, now let's go to a break, but let me make this one point here, and that is this. This relationship is going to be ridiculously important for the rest of the course, what we've now proven. This one, a contraction of forward velocity with itself, is equal to -1. We call this the normalization of forward velocity.
So the contraction of a 4 vector is with itself is -1.
Of this particular forward
Ah,
vector.
or this.
Yes,
okay,
no,
okay.
not all. No. Other forward vectors give you all kinds of other stuff. This one gives you -1.
And does the operation of contracting with itself have a name?
Well, in normal linear algebra, you would just call it measuring the length of the thing, yes, because it will be an inner product.
Okay.
So some people call this the length of the forward vector in Minkowski spacetime.
Okay.
But you know that's his nomenclature.
But isn't it, if we include c, if we don't include c as 1, then it's -c, no?
No, then it should be -c squared because this
Minus
is the
c
unit
squared.
of a velocity,
Okay.
and it's a product of two velocities. In units, it's contraction, but it's in units. So if you were to put the c's back in, it would have been -c squared. Now again, this one is going to be ridiculously important for a lot of things we're going to do. So make sure that you have this somewhere. The normalization of forward velocity, as it is called. Now with this one, we're going to do this beautiful exercise, but let's have a break first. Yeah.
You need to say something nice. I did that already.
Very extraordinary.
With my
So
oh my god.
boring.
What is this?
can choose.
I was eight.
The other one is
My
brother,
brother.
with
Your
natural
brother.
language
Oh, your
processing.
brother.
Processing is what is mathematics simulation.
People, I propose we continue.
Yes.
Yes.
So let me take my delimited book here. Listen to the first half. And let's go to exercise 6, chapter 5.
Okay, that's a very passionate way to turn yourself.
Again, this normalization of forward velocity is going to be extremely important. So make sure you have that, and the derivation that we just did, that you don't have to worry about this for the rest of your lives. Okay, so this is an exercise where they say consider a particle moving along an x-axis whose velocity as a function of time is given by such and such. Let's write down that thing.
Just one thing again,
Yes.
is the velocity in tensor form always given as u?
Yes, yes, this is always very clear what they say. If they do the tensor version or the 4-vector version, they will always write it as mu. So this one is, well, going to our example with Marit and Severino, which is walking there. This is what we would actually measure, yes? This is our amount of distance between two events, them being there and them being at the coffee machine, that amount of meters, divided, mathematicians hate this, but divided by the amount of time that we saw them take to go from one event to the next. Now, and apparently it's given by this equation. Okay, well, that's easy enough. So no relativity there, this is just Newtonian physics if you want. So, let's start easily. G is some constant. It's always G, right, in these things. Does the particle's speed ever exceed the speed of light? That's question 1. How can you tell?
Because the speed is the one on the left. So
Yes.
if you look at it, if t grows, the numerator and the denominator grow equally, kind of, to infinity.
So there's a good point. If you would take t to infinity, you would get gt over, well, this obviously will win from the 1, right? So this is by very good approximation this. So might as well drop the 1 if you're going to make t infinitely big. And that gives you gt, and it gives you 1. And 1, here's our unit thingy again. It should be a velocity. We left out some c's. So obviously if it says 1, but it should have been a velocity, this is where the c had come back, right? So it says here, yes, this velocity goes at t is infinity to the speed of light. Could it be that there was maybe somewhere in between now and infinity time a moment where it had gone spiked beyond c? Because your argument now is very far in the future it will not exceed c. That is very true. But could it have exceeded c somewhere in the meantime?
No, because it's
No,
How can you tell?
the same thing over the same thing, so that the one, like, they grow at equal rates at all times.
No, certainly not at the
And
beginning.
also the denominator is bigger than the numerator.
Okay. There's okay. That argument I find very, very nice. Yeah, that's good. I mean, I think you were all saying the same thing, really, but just in different terminology. I mean, this one is indeed always bigger than the numerator. So you always have a number divided by a slightly bigger number. So that's a very good argument. I was a little bit more highbrow, unnecessarily so. I noticed that it was a monotonically increasing function. That it's a function that always increases. That's what I did first. I first proved that this function will always become bigger at t when t grows, and therefore the biggest velocity is when t is infinity, and that one is not bigger than c, so therefore it's not before. Yours is much better, okay? But both of us are correct. Okay.
Putting it equal to c, that equation,
Yes.
would that also be a strategy that would give you anything at one point? Because I didn't really get anywhere with that.
Okay. Well, as in you put it equal to c.
Yeah, and see
Well,
if you get something that's
It
impossible.
would have been 1, but in the c is 1 unit, sure.
Yeah.
And then what did you do?
Just work out at what t this velocity would be equal to c.
What did you find?
I got some math and it just became larger and larger.
Okay, good. Now, I think that is a good strategy, because what you're asking now is, now suppose that it does hit c at some point, the speed of light. At what time does that happen? If you find that there's no moment in time, that there's literally no solution to this problem, there's no t for which that happens, then you've also proven it, yes?
Yeah.
So, and yes, if you would go through this, you will find, just by doing the algebra, that this only happens when t is infinity, which is another way of physically saying that it never happens. Right? If you have to wait an infinite amount of time for something to happen, that's another way of saying it won't happen. So I think we have a couple of strategies to show that this is the case. So whatever this motion is, let's keep Severine walking to the coffee machine. Her velocity will not go faster than light at any point.
We just find that's false.
Good. All right. So now they're asking for this one, more velocity. Suggestions. First of all, how many numbers are they asking for?
Well, the components are
How many are those? It's 4. So they're asking for 4 numbers here. Now, I'm sure that at least 2 of these numbers are straightforward.
Y and Z.
Yes, because they're not moving in Y and Z direction. Now, of course, you might make a point, but wait, this is 4 velocity. It's not this one, so they might have a velocity in Y direction and Z direction in R units, R time and R distance. But maybe this basket object, R distance, their time, maybe they do pick up Y and Z velocity. Right, do you see that in principle you could ask that? Do you all see that the answer is still 0? What's the relationship between Uy and Vy?
Oh, it's just divided by d tau.
Well, this one is dy d
Oh,
tau.
no, it's
This is d.
It's a gamma factor.
it's not.
Yeah. So, and if you know, if we are given that these are 0, well, the gamma will certainly will not make it non-zero. Okay, so just a small point. The velocities in are well, let's give these things names. Let's call this usual velocities for now on. It's a little bit easier talking. So the usual velocities are 0 in Y and Z direction, and because of this, then it also will be the case for the proper velocities, the 4 velocities. Now we still have 2 to go. We have this one, or 1 and 0. Suggestions? You're asking for these numbers.
Well, U0 is, I think, always the same.
Okay, what is it?
Gamma.
That is true. U0 is just dt d tau, yes, by definition. And dt d tau, by time dilation, is just gamma. Is gamma constant, by the way, here? Is it?
I mean, it's
Changes with
oh no, the velocities.
Yeah, there's a velocity in there. This velocity, the usual velocity, is somewhere in the gamma. So the gamma is certainly not going to be a constant. I'm wondering if somebody's now making a huge objection. But wait, we're doing special relativity. How can velocities? Sorry.
Acceleration.
There isn't. Apparently the thing is accelerating.
Yeah.
Are we doing special relativity?
This is special relativity.
Oh.
Yeah.
Well then,
Doesn't work.
doesn't make sense.
Does it or doesn't it?
No.
Maybe we select one point in time.
Certainly at any point at one
It's still
particular point in time, the velocity will momentarily be constant. Yes, that's true. But it's a very lean theory if you can only look at very small moments in time. So are we breaking special relativity here? Are we allowed to use special relativity? What's going on here? I mean, we have something that accelerates. Marit or Severine is accelerating towards the coffee machine as a normal person would on Friday morning. Right? I mean, so are we breaking special relativity? Are we allowed to use special relativity?
But is what is the name of the person?
Marit and Severine, one of the two.
Yeah, is this person the famous?
Wow.
They have names, Giovanni. They're not just objects. But your question is?
Is Severin the frame of reference?
No.
So it's an external frame of reference,
Yes.
and it's an inertial frame of reference.
Who is an inertial frame of reference?
The observer who sees is the
Yes.
Severine
Oh,
accelerator.
true.
Yes.
So we can use it.
Yes, as long as we stay in an inertial frame, we can look at accelerating things. As long as we don't accelerate ourselves, we can look at things that accelerate.
But their d tau
Yeah.
is their proper time
Yes.
as they accelerate.
Yes.
So we're still looking.
So we're using special relativity.
No.
In
Only
their
if I go
case.
to no. D tau is invariant. So whatever d tau you can transfer to any system that you
We
want.
can use d tau as well in general relativity.
Absolutely. Yes. No. A problem would have been if we were to decide to go to their coordinate frame and try to calculate stuff from there.
Yeah.
Then there would be a problem. We're not allowed in special relativity to transform to their coordinate frame, but we're certainly allowed to look at them from our coordinate frame. That's what we're doing. This is the whole business of inertial frames, yes? Special relativity holds if you, as long as you, the observer, is in an inertial frame. The thing that you look at is perfectly free to accelerate as much as it wants. Right? Now, I made this point a couple of times in special relativity the course, because there really is a extremely pesky misunderstanding, unfortunately, about special relativity, that you're only allowed to look at things that go with constant velocity. Jacco, in his particle accelerators, CERN and such, he literally never uses general relativity. Even though he has a particle accelerator. Special relativity holds for him perfectly fine. Not by approximation, no, exactly, aside from curvature of Earth and actual general relativistic effects. The acceleration of the particles is no reason for him not to use special relativity. So this is perfectly allowed. So we have a gamma here, it's just not constant. And what does it do, by the way? Does it increase? Does it decrease?
It does increase.
It increases? Yeah.
Well, we said that it was monotone and growing.
Well, V was, yes.
So it decreased. No. Yeah.
Yeah, but it's 1 minus V. So you subtract a bigger number in the denominator, so you divide it by a smaller number, so the outcome is bigger. Yeah. That's a mathematical statement. Okay, let's make it physical. We already saw that sibling or Marit or person is going faster. And you know from your special relativity, if you go faster, the gamma goes up.
Exactly.
So this one will itself go to infinity at some point. It's not a constant. Good. But we know that it's gamma, we haven't calculated the damn thing yet. So how do we do that? What is the expression for gamma in this case? That's a U0 that we're looking for. Suggestions?
Use that V.
Yes. Because of course you know that your gamma is just this. Oh, you have your V here. Might as well put it in. Alright, so yeah. 1 minus gt squared 1 plus gt square root. Okay. 1 plus gt squared gamma 1 is 1 plus gt squared square root. There you go. And this is algebra. Just put in the V that we were given, the usual V, the not for velocity V, work through the algebra. Notice that at t is 0, gamma is 1. That agrees with special relativity. That when Marit and or Sylvie were not walking yet, they and us were still in the same coordinate system. And that means their time is our time, so there should be no gamma. Their dt and our dt should be the same, which is the same thing as saying gamma is 1. That is true. At t is 0, gamma is 1. So when they started walking, our times were still flowing as quickly. But as they accelerate, unfortunately, it becomes bigger. And it becomes infinity just as we already expected. All right, we have the ux, the u1. So this one is taken care of. How about u1? Suggestions, as they say in some country. Suggestionen. Yeah.
Yeah.
No.
Got to think about it actually. Vorschläge.
Oh, Vorschlagen? Yeah. Okay. The thing is, if I try to speak German, I just take the Dutch word and Germanize it. I'm sure the Dutch people recognize this very well. Yes, from your German language.
That's exactly what
you just take the German word and you. Yeah.
Wow.
Okay, so Vorschlagen. What do we do? We need the u1. So we need dx d tau.
What Zef said before, it's just gamma v.
Certainly one way of doing it. Yeah, we can just do this.
We already have the
We have the gamma. We also have our v, that's this one. Something beautiful happens here.
It's GT.
Yes. GT. GT. So what we get here is 1 plus GT t squared. And this is GT. Okay. Okay, good. So this is exercise B, yes? Now, just let's do a little bit of physics on this. This goes to infinity. The proper velocity goes to infinity. So things go faster than the speed of light, apparently.
I mean, this is an unrealistic situation.
In what sense?
The fact that you would have to use an infinite amount of energy to be able to keep on doing this.
If you want to get an no, I don't need an infinite amount of energy. Why?
I mean, for that v to be true, and our assumption that it even can go to 1, so c, we would have to apply an infinite amount of energy to the system.
I don't see how, because this thing here, the question is, can this become bigger than 1? That will be c, yes, in our units. So the question is, at what moment in time does this become 1 or bigger?
I mean,
now certainly this happens when this happens, yes? And
so we can still choose our g to be...
Oh, g is fixed. It's a given number. You don't have any fixings to do there. And what I just see from following the math is, there is a moment in time, and it's not infinitely far away, where t is such that the velocity, this velocity, exceeds the speed of light. So no infinite energies, no infinite amounts of waiting. It looks as things go faster than the speed of light.
But isn't that just the change in distance, not velocity? Because the dt also becomes infinitely big, so...
Also that is not exactly the v, is v gamma.
Yes. I mean, that's the whole point, yes. This is not the velocity that you would measure from your frame. It's your amount of distance divided by their amount of time. So you don't have to worry about this thing becoming bigger, because you're not going to measure this anyway. In fact, nobody's measuring this number. The measuring you do with the two numbers from your own coordinate system or their own coordinate system is certainly not a mix of both. So that this thing goes at some point bigger than 1, no problem in physics whatsoever. This one doesn't, because that's the one that you actually measure. No problem there. Alright, now, let me smuggle in a little exercise B2 here that the book does not ask for, but I think it connects very well to what we were doing before. What should this be? What is this number? That's -1. We proved that for a general case, so it should also hold here. Let's check if this actually fulfills that condition. We proved this one, the normalization for velocity for all cases, without specifying what was moving and whether they went to coffee machines and what acceleration. This should be always true. Let's check if our particular situation agrees with this. Vorschlagen.
I don't know what it.
Well, my German vocabulary has doubled today, okay? So,
Suggestion. Oh, suggestion. Okay.
Or you just do the same thing that you did before and fill in numbers.
okay. So what did we do before?
It's a pretty good question.
So the first term squared plus the second term squared. Yeah, that's it.
Yeah, plus, minus, plus, minus, minus, plus.
Minus.
There is a number of
How about this?
minus.
Let's make them both as such, yes? Okay, that was the same thing we saw that before. And this one, for the double contraction, becomes a minus when mu and u is, so this one. Oh, and we have to square it, because it's mu0 and a mu0, together with this -1 gives you...
It's crazy.
Okay. And then the next term in our double contraction should be mu1 squared with a plus sign in front. This one squared.
This is 0 and then just the square root.
Minus 1.
Okay, just to check that this rule is obeyed. Now, if you find yourself in an exercise or you're doing research in general relativity or whatever, and you have some particular way of motion, and you do this check, and it does not give you -1, then that does not mean that you've broken general relativity or that you can pick up a Nobel Prize. It means that your starting expression was wrong. It was never in agreement with relativity. So, if I were to write down a random function v as a function of t, even if I make sure that it can never exceed the speed of light, right? I can probably think up a v that is some strange combination of t's and such that will never go faster than the speed of light. I might find by doing this check that its contraction with itself is not -1. In that case, it simply means that my starting expression is not in agreement with relativity. So this normalization for velocity is a check, if you will, whether the calculation that you're doing is still okay with relativity. This we got from special relativity. We never put anything in, not what we were looking at, whether we're coffee people or whatever. We just said, just from space-time itself, this should always hold. So that means if you find that it does not hold, you're broken space-time. One other way of saying the same thing is, everything in space-time should obey this. You will never ever find an exercise in real life, not just an exercise, you will never find physics in real life that gives you a v that does not obey this. So the exercise didn't just give you this, they already knew that it is in agreement. So it's a good check for yourself. You're doing research in general relativity, special relativity or so, you find yourself a v from some place. At the moment that this is checked, you have to go back to the drawing board. You made a mistake.
Has this been tested empirically?
This one?
Yeah.
Yes. In fact, it's going to get to a beautiful answer at the end that the book doesn't point you towards, but I am going to. And then you will see that this is actually much more familiar than it might look now.
Okay.
If this, I mean, you're saying that if it isn't -1, it's definitely wrong. Does that it is -1 mean that it's definitely right, or can you still?
Well, no, it's a necessary but not sufficient condition.
Okay, so
yes.
All right.
I mean, again, the point really here is that this was proven just based on properties of space-time alone. So everything in space-time should obey this. Okay, so this is given. What is C? I dropped my book somewhere. I think I remember.
I thought the question was what was C, like 300.
3.0 10 to the power 8 meter per second. Yes. Or as we call it in the business, 1. Okay, the next question, if I recall correctly, is calculate t as a function of tau.
X and t is a function of time.
That's what this is, x and t. Okay, so these two we have to calculate. Right. Now, first of all, do you see the question? Yes. What they want us to calculate with this one is, okay, suppose that you know what time it is on Severine's clock as she was accelerating towards the coffee machine. How can we take her time and turn it into our time? That's the function that they're asking. No, that doesn't work. No, that's a good suggestion, but that one does not work. So Tom is saying, we'll do it by Lorentz transform. Take their time, Lorentz transform it to ours. Why doesn't that work?
They deal with general relativity and we with special relativity because they accelerate.
Yes, the Lorentz transform only work between two inertial frames, and they're not an inertial frame.
Well, we know that dx d tau is gt.
Dx d tau is dt, yes.
Right.
I'm not seeing where.
It's in the
Here,
forward
yeah,
direction.
dx d tau is dt, sure.
Can we integrate? No, but then you have a function both in
Yes,
t and
yes,
tau.
yes, yes. So you see that there's an issue, yes. But let me emphasize a little bit Tom's point here for a moment. The obvious thing to think about is when you see you have to calculate some guy's time, woman's time, into our time, you think immediately of a Lorentz transform. That would be okay if their time was also measured in an inertial system. They're not. They measure time, but they're accelerating. So that means their time is not inertial time. It's still called tau, but it's not connected to us by Lorentz transform. So Lorentz transforms do not work here. We really have to do something else. Now Simon had a suggestion. He said, well, we know how, let's take this one. It was this one, right?
Yeah.
Okay. He said, well, let's do the following. It's dx d tau, that's by definition. So we know that, and this is gt. So we have the x that we're looking for here, that's this one. As a function of tau should give you gt. Okay. And that sort of gives you the impression, oh, but you know what, then it's probably something like this. Agreed? Because this guy's derivative is gt. It's just that this is t and this is tau. So,
I mean,
and t and tau are themselves.
You would have a tau, but maybe from the first one you can also get a function of t and tau, and then you can substitute.
Okay, but you see here, and you're completely right. I mean, this would be a strategy. What you see here, this doesn't work. Yes, you're integrating with respect to the wrong tau, to the wrong time. But and in order to get the right times everywhere, you need the connection between the different times. That's another way of saying you cannot solve this one without already knowing this one. It's a coupled system.
Could you get a function in terms of dx, dt and d tau and then split it?
Yeah, that's the question, yeah. Can we? Can we though?
I mean, I wouldn't see why not.
Try to give it a spin?
I'm good now.
Okay. I'll be a scriber, but
Just that I don't know how doesn't mean I know.
I mean,
how.
so you know that dt d tau is 1 plus g blah blah blah. Yeah.
oh, this is something we can work with people. Look. This we calculated, yes? So this, forget about this one for now. We get this, and what we want is t as a function of tau. Well, that's sort of in there because there's t, there's a tau, there's a t. That looks like something that can be solved. In fact, let me do it like this.
Sorry?
What if I rewrite the equation a little bit like this?
Exactly.
Yeah? That's really just what we had calculated, written in a different form. So I know, if I know an infinitely small amount of time that we wait on our clock, and I know their infinitely amount of time of walking, I know how those are connected, but I don't want infinitely small amounts of time, I want the full one. So how do we get from infinitely small to non-infinitely small? This is when integration. So what is d tau integrated?
Tau.
That's what we would call tau. Okay. What is this integrated? Electrodynamics people should know this one because it just so happened that we had a similar thing constantly in electrodynamics when we solved the Biot-Savart equation. Mathematically happens to be the same thing. I noticed on the train yesterday.
Some arc then.
No, arctang would be without the square root.
Oh yeah.
1 over 1 plus x squared is arctang.
What's the other one? Which
Hyperbolic sign.
And hyperbolic sign, thank you. It's an arc hyperbolic sign. Do we all remember that you have something like this? If you integrate this, you get the inverse sine of x.
Yeah.
Okay? The only thing that we have done now is that we said, you know what, here's a minus and here's a plus, but otherwise it sort of looks the same. But what if we replace this x by I times x? Then the I squared would give us exactly this, yes? So the answer apparently of this one would be the arc sine of I times x. And the arc sine of I times x is what we call in mathematics the hyperbolic arc sine. And this is Natalie's point, I think. You get this.
I'm thinking if we would have used the GT term, could we also have found the solution if we used the chain rule on the xd tau to get the terms in terms of dt and then fill in the same stuff?
I think so, yes.
Would have
There's
also
another way
worked.
of doing it, yes.
Okay. But then you get an x in there, so
yes, so
not sure.
not sure. Do not show you. This certainly works. So.
Mm.
But then again, what we now have is, if you have t, you can calculate tau. That's not what we're looking for. We're looking for the way that if you have tau, you can calculate t. So we have to write this in terms of t something 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 tau. Hard part is all the integration is done.
Well, then it's the hyperbolic sine of gt, g tau over g.
Yes. You get this hyperbolic sine. It's obvious. Yes? I mean, the inverse of the arc sine is the sine itself. Hyperbolic. Are there people who have never seen a hyperbolic function at all? It's fine if you haven't, but because it just requires a definition. That's all. Okay? Because then all of a sudden from here to here might be a little. Where does that come from? Yes.
Is it 1 divided by g in front? Or
Yes.
G?
1 divided by c.
Yeah, I would also say it's g. Because you multiply
Why
both
is it
sides
not
with g.
No, because if
there's
I,
a g in there.
I multiply this both sides with g,
There's already a g.
then I take the sine,
Yeah.
then I get gt is the sine hyperbolic sine of tau g, and then I have to divide
then
this g. That gives you that
Mm.
one. Now, just a matter of definition, guys.
So
A
symmetrical.
hyperbolic sine of x is by definition, really there's no physics or mathematics involved here, it's literally definition of the thing. It's by definition e to the power x plus e to the power minus x. That's just the definition of the thing. That's all it is. Yeah. Yes, very little I can add to it. You can prove, in fact I might even put it on a layum just for completeness. You can prove mathematically very simply that going from that's the integral from 1 over the square root of 1 plus x squared is the inverse hyperbolic sine of x. That's what we use here. By the way, we have the solution now. Okay? We can now take their time, tau, calculate it to our time, t. That's what we have here. So we're halfway there. What happens to, let's do some physics for a moment, we have the mathematical solution here. What happens if tau becomes really big? So for them it takes a long time to go to the coffee machine. What happens to what we measure?
Also takes a long time.
Also takes a long time, but for us it takes even more time, right? Because if they take a long time, that's tau. We take their time to an exponent that becomes ridiculously big.
Because e to the minus x doesn't.
No, the e to the
Doesn't
minus
affect-
dies
doesn't
out,
become
right?
constant,
I mean,
yeah.
if their time becomes big, then this one dies out. This one becomes really big.
Right.
So it means that the amount of time that we see for them to go to the coffee machine becomes ridiculously much bigger time than they themselves see. Is that surprising in light of relativity? You will hear by the tone of my voice that I hope that the answer is no. Is it surprising for you to hear that us seeing them walk to the coffee machine for us takes longer to see it happen than they for themselves? This is exactly time dilation, right?
Mm.
But it's exponential, it's kind of surprising for
Well,
me.
the exponential part simply comes from the fact of
Yeah.
this.
Yeah, I mean, I see why, but
Yes.
I still wouldn't have expected it.
That it is exponential. No,
Yeah.
I agree with that. No,
Is
that's
that also because general relativity comes in at some point?
no, there's literally no general relativity in this whole exercise. From beginning to end, there's none. It's all special. Again, only if we try to get our numbers and transform to their numbers,
Mm.
this is when we get to general relativity. So, but this is, I mean, you already knew if they had been walking with constant velocity, then the amount of time that we saw for them to make the trip was longer than their own time. Yes, this is just normal special time dilation. We have the same effect here. It's just that it takes longer still, not because of general relativity, but because their gamma increases in time. So no surprises here. Let's do x. Suggestions. We have
Yeah,
one.
just fill in.
Then I would use the U1
So U1 is GT, yes?
Yes, and then do the chain rule on the
Yes.
dx dt d tau dt.
That is a beautiful suggestion. Let's do that. We know that dx d tau, here's the x that we're looking for. We had calculated it's given by gt. That was a crappy thing. We could not integrate this because we had it said t on the right side and not tau. But we can turn this t into a tau with this one. So it is gt. The t itself is this in terms of tau. So dx d tau really is the same as sine, hyperbolic sine g tau. Can you integrate this? Can you turn this into x as a function of tau equals to 0? Yes, you can. Yes, you can. Yes, you can. Let me make things easy for you. You have trouble integrating this. This is the definition of the sine, hyperbolic sine, yes? It's just two exponentials. Tau means integrate this. You have trouble integrating exponentials.
But there is a minus there. There was a plus there.
There is no minuses. Oh, I'm so sorry. This should have been a minus.
Oh, okay.
Excuse me.
Okay.
No, what I wrote down accidentally was a hyperbolic cosine. Sorry for that. It's a minus.
So then you get a plus overall. And then there is a g factor.
Okay. Now, mathematically speaking, people know how to do this, yes? It's just the integral of these two exponentials. I mean, it looks so complicated. It's hyperbolic sine. Oh, I don't know how to integrate it. No, it's just two exponentials. And exponentials, it's easier. Yeah, I mean, if there's one thing is easier to integrate, it's that. So, tell me what the answer is.
1 over g.
Okay. E to the power g tau, I would say. That's the first one. How about the next one?
So it's plus c to the power minus g.
Just the hyperbolic cosine.
This, indeed,
Yeah.
aside from the g, is by definition the hyperbolic cosine.
Oh yeah. That makes sense, yeah.
Again, no deep physics or mathematics here. It's literally just definition of the word. And of course, it's defined that way because it's reminiscent of normal sines, yes? The derivative of a sine is a cosine. So they defined the derivative of the hyperbolic sine as the hyperbolic cosine. So, we now have exactly what we're looking for. This is 1 over g hyperbolic cosine g tau. This is exercise C. All good? So, aside from mathematical steps, what we did was we took the v, we used it to calculate the forward velocity. Then we were asked, well, give t and x as functions of tau. Unfortunately, the t's here prevented that step. We had to write the t's as functions of tau. That we did by integrating this one. That gave us this. And because we can now write t as a function of tau, we can solve this one. That gave us that. My feeling is what we are time-wise.
Yeah, it's 30 now.
Exactly.
Okay. So, let's make one final step. It only takes a second, but it's so beautiful how things are now coming to come together. We now know this is our solution. I promised already that this is really just physics if you are familiar with it. It just doesn't look very familiar at this point. Let's make it familiar. We saw here that if you wait very long, then they are going to go to the speed of light, yes? We already saw that. That happens in their frame, happens in our frame. Now, if you are with the speed of light, then special relativity is important. But suppose that we don't wait as long. Suppose that we don't wait so long. They have velocity, but not speed of light kind of velocity. You should end up with something Newtonian, agreed? If you take special relativity, but you don't go really fast, this should just become Newtonian physics. So let's turn this into something Newtonian. Now, Newtonian happens when v is small, but v is small when tau is small, agreed? So, let's make the approximation. This one, a final marker. Let's make the approximation that tau is a small number. What happens to tau itself if tau is small? I'm sorry, when tau is close to 0. So you don't give them as much time to accelerate to the coffee machine. You give them time, but not as much time. What happens to tau itself? You might notice from your special relativity. You could also read it up from here if you want. What happens to tau at the moment that you make?
Wait,
To T or
tau?
Yeah.
Tau is the one we're making it 0.
Yes, but tau itself. No, you're right. I'm not phrasing my question very correctly. We all agree that tau goes to 0. Yes.
Mm-hmm.
So that means they're accelerating, but you don't give them as much time. So that we should end up with something Newtonian. From your special relativity, you know that if t and tau are the same, or you expect that t and tau become the same.
Yeah.
Well, that does happen though, because if you make this very small, then remember the hyperbolic cosine is to the power g tau minus to the power minus g tau. Let's do a Taylor series. Let's say the tau is small. That's our whole idea. Let's go to low velocities. Tau is small. You know what the Taylor series is of an exponential?
Just
The exponential itself multiplied by 1 over the...
There are more terms, but this is the first term. Okay. Let's do that here. So, if x is small enough, this is a very good approximation. Now we're going to make Rx, which is d tau, we're going to make that small. So what does this become?
1 plus gt.
1 plus g tau.
Tau, sorry.
What does this become? Minus something something.
1 minus g tau.
1 minus, but this minus
Yeah. Cancels the other minus.
cancels the other one, yes? So I get plus g tau. Gives you, these cancel. I get t g tau, g gives you tau. So apparently, if you don't wait too long, they're not moving as fast.
T and tau.
T and tau are going to be the same number. That's correct. That's what you would expect on Newtonian arguments. What happens to x? Let's make the same approximation. You have x here, 1 over g, and this has to be Taylor series.
Why do we have to use the tail? Like, why wouldn't it be possible to just say, well, tau's approaching 0 and keeping it exponential?
Because then this would have become 0.
I mean, yeah, but
Well,
why
x-
is it mathematically not doable?
X reaches 0, right? Approaches 0.
Yes. But if you make it 0, then t becomes 0, which is correct. But it's hard to do physics if you don't let any time pass. So we're going to make tau small, but not so small that it's actually 0. This is why I do the Taylor series.
Oh, okay. That makes sense.
Let's do the same thing here. Because this one simply becomes tau at low velocities, exactly as you would expect on the basis of special relativity. Let's do this one. So x is this, right? Hyperbolic cosine. Let's make it Taylor series. You tell me what happens. 1
Plus g tau
G tau.
plus 1 minus g tau.
Okay. And oh, and there's 1/2 here.
So it becomes 1.
Yeah. It becomes no, it becomes 1 over g, right? That doesn't feel right. That means they're at one position.
Well, it becomes
It's a
G.
constant.
one.
So they're not moving, or what?
Well, at
Hardly
this
makes sense.
t is almost 0.
Yeah,
Within
so
this time, they're not
and we
moving.
know that at t is 0, they hardly have made any acceleration. So of course they're going to look as if they're just going to be fixed in one place. But how about we just add another term to the Taylor series? We give them a little bit longer to move. It's the second term to the Taylor series, right? We all see the issue that if you make x small, if you make tau small, the velocity small, then in space it means they're hardly moving. So let's give them a little bit of time to move to add an extra term, that's this one, to the Taylor series. So I left a little bit of space open here. you fill in the details. What happens here? Squared, squared. And there's a t. Now, okay, how about this? What happens here?
Minus. Oh, no, it's
not
plus.
minus, it's still squared. Because you square the number, so you get t squared. Tau squared over 2. Okay. You still, if you drop everything out, you still get your 1 over g, that was their original starting position, plus 1/2 g tau squared. That's what you end up with. But tau was itself close to t, right? So this gives you 1 over g plus 1 over gt squared, normal t squared, by good approximation. Does it look familiar to you from your high school? Now, can you name something from Newtonian physics? Because we're now in Newtonian physics. Can you name something in Newtonian physics that moves according to 1/2 gt squared?
Acceleration.
Yeah, but not just acceleration. Free fall. All of this was just people falling towards their coffee machine, but secretly written in special relativistic terms. But you only saw that when you went through the calculation and then made things Newtonian. And you said, oh, wait a minute, it's just free falling stuff. So here you see something falling in gravity, but described by special relativity. No general relativity required as long as we don't move ourselves to their frame. Alright, so people, we're not going to see each other next week, because next week, yeah, I know.
Wait, what?
No, next week, Osa sent an email that, because Friday is a day off for some crappy reason.
Yeah, I don't know why. What the hell? It's super strange.
I don't know, because I could have used
What
that
about
week.
Tuesday?
Because we're 7 weeks instead of 6 or something.
Yes, but and the reason for that
You
is
see
that
what
Osa
it
sent me an
said
email and
on
they
that
said, well,
thing.
Friday
Why
is
we
going to drop
just
out
have
because of some
holidays?
general day, and then she said, we might, then she said, and therefore we're also going to cancel.
This
That's
is
a
so
good
weird.
reason.
So we're free on Tuesday, Wednesday, and Friday.